There we go. Okay. So there's that. Oh, okay. Do not want to exit, just want to minimize. Okay.
Unless you guys are so fast.
Slide everything off the rack and
You know, see what's supposed to go folded?
Yeah.
And then they just
tries them on.
Also very sexual.
You're looking for a large size, throw the other two on the top away and get the one.
My favorite character is Poe.
I love Poe.
Poe is absolute my favorite.
Teletubbies?
Altered Carbon.
I love Poe. Honestly, Bing was a little bit more better in case. It's better written. It kind of went downhill, honestly, after the third season.
Dixie, Lala, and Poe.
Okay. All right, we're finally here. Ooh. That took a while.
Wait, we're in the science, isn't it? Oh shit, we're in the science area.
What?
We're in the science area. Science area is right over there.
Yeah, science area is right over there.
Okay.
Did you just get a new text?
Yeah.
What does it say?
Now it's in the science area.
Emergency update of responding to crime in progress in the science area of campus. Avoid the area. Well, the science area is across on the other
It's the
side.
chemistry one right here, isn't it?
Huh?
It's the one right here.
Yep.
That's right.
But they don't specify the protocol. They don't say, okay, if you're near the area, evacuate, go home. So, I mean, do you guys feel safe enough to continue class, or do you?
Yeah, we're fine. It's cool.
We're fine. Okay.
I don't think we can do lab today, though. We gotta go home early.
Yeah.
I just got a message from the ARC trying to call me.
Yeah.
Oh, I see.
Call back the ARC number, like, yo, what's up,
Yeah, they obviously need to.
Everyone's phone's gonna go off just so you guys. ARC's calling.
Is there a new message? Is there an update?
Yeah. I don't know what the thing says. I think it called.
No, it's still the same. It said in progress in the science area. Avoid
I didn't
the
see anything
area.
when I came in right now. I didn't see anything when I came in.
You probably don't want to see it, right?
The sheriff told you it was clear. It's probably clear. It's probably outdated information.
That's what the sheriff said. Was it's outdated, and as far as he knows, it is clear. Okay. So here's the share folder. You guys can access the share folder as well. And just double checking to make sure the door is locked.
Oh, it's locked. I tried to get in.
It's locked? Okay. Are we ready?
I'm ready.
We're just being nerds over here.
Okay.
As long as we're not gonna get shot, I'm cool.
Okay, so what we'll do today is we'll take a look at the at exam one from last semester, and if we have time, we can also look into the exam one of the semester before that. So if you go to the share folder, go to old X1 or exam one, and these are all quote unquote numbered. So 1179 is the fall semester of 17. It looks kind of strange, but this is actually how the entire district code semesters. So the first one is always going to be there because we are past the 1900s. And then you have the year, 17, 16, and so on. The 3 means it's a spring semester. The 9 means it is a fall semester. If you ever hover over hyperlinks of your classes, you will see those code as well. Obviously, most of you have not attempted to hack the enrollment system. Because if you had even logged, you would have discovered these codes. And don't ask me why I know that. I cannot answer that question.
I'm sorry, sir.
He swears.
Can you repeat that?
Security ever.
I'm streaming right now.
Can you look right up to the left into the thing?
I only claim this. I am just curious. Okay, so the exam would look kind of like this. Okay, so the format is, the first page, you put in your last name first. Okay, your family name / surname goes first, and then your given name or your first name goes second, and then your student ID. Okay, because this part is really important. If you bring any extra pieces of paper, or if you use extra pieces of paper, make sure that each extra piece of paper also has your name, so that in case I lose track, for whatever reason, I can associate individual pieces of paper to the person. All right. So obviously the time and the place will not be the same. Okay, we don't have room 121 anymore. It is open book and open notes, but no electronics other than a scientific calculator. A graphing calculator is fine. Okay, so if you have a graphing calculator, that's okay. If you have a more primitive calculator that cannot graph, that's okay too. But a scientific calculator app running on a phone is not okay. All right? So does anyone need to buy a scientific calculator just because of that? No? Okay. I was hoping somebody would ask, then I can just say, go to the Dollar Tree. You can buy a scientific calculator for $1, for $1.
Not scientific, but for function.
No. Actually, scientific calculator, sine, cosine, and all that stuff. Yeah.
Oh snap!
Yeah.
I'm gonna pick one up just for fun.
Yeah, but only at the beginning of a semester of an academic year. So back to school, you have sale.
Oh.
Yeah, but only for $1 because it's a Dollar Tree item.
We'll go buy them and hustle them.
Okay, so you might want to bring extra sheets of paper. Okay, because some of you may need that. I cannot supply additional sheets of paper reliably. Okay, I might bring some, but it is better if you can bring your own. Write legibly, which means you need to make sure that your handwriting is clear enough that I can read it. Okay. Ready? Okay. Questions have equal weight for this one. If they do not have equal weight, I will let you know as well. And I'll also let you know how many questions in total, so this way you can plan ahead of time at the beginning of the test. And the exam accounts for 20% of your final grade. So this is the first exam. So it's 20%. The second exam is 20% as well. The final exam is 40%. So are we okay with all this stuff? Okay, all right.
So the number of questions will vary, right? It won't necessarily be 5.
Can potentially vary. Yep, it depends on what type of question, whether they're time consuming or not. Yep.
So are the questions? Can you get like half credit, or like is it either 0 or 100%?
Everything is graded based on the grading scale that I talked about at the beginning of the class in the syllabus. In other words, for each part of the exam, for most parts I should say, there will be 0 points for nothing turned in, okay, or the question is skipped, or whatever I'm looking for is completely absent. There will be a 25% of all the points. If I can see something, it barely resembles what I'm looking for, but it is incorrect, okay? There's 50%, which is basically, so this is an F, this is a D, this is a C. So the C basically means, I can find the most crucial part that I'm looking for. It's there, but everything else is wrong, okay? So just barely, you're getting the core concept right. A B, which is 75%, is basically saying everything that I'm looking for, the core part is there, and then the other stuff is also there, except it's not perfect, okay? It's good, but not perfect. And needless to say, an A is 100%, which basically means everything that I'm looking for is there and it is done correctly. So a B typically would be close to an A, but with careless mistakes or omissions of some kind, but it is not crucial to bump it down to a C. Is that okay? So every single question will be broken down into multiple parts, and then each part is using this particular scale. So the answer to your question is yes. So for most things, there's partial credit, but whether a particular answer is going to get partial credit or not really depends on what the answer has and what I'm looking for. Okay. All right. So let's go ahead and take a look at some of these questions. So the first one says using the carry, borrow, look ahead design, an adder and a subtractor are very similar. Okay. So do you guys remember that part? How an adder and a subtractor are very much the same? The only difference is how the G and the P terms are defined. In the spirit of the RISC design paradigm, RISC means reduced instruction set computer, and I think we talked about RISC. Did we?
I don't
No? Okay. So so I probably won't mention that. It makes sense to combine an adder and a subtractor into the same circuit because the structure to compute the overall carry, borrow, and the sum difference is the same. So the rationale of why I want to combine the circuitry can be, that's not really important, okay? Knowing that for adder, GI is XI, YI, PI is XI plus YI. So once again, make sure that you remember that this multiplication is really a conjunction and this addition is really a disjunction. Whereas for subtractors, GI is the negation of XI and YI, and then PI is defined to be the negation of XI or YI. Is that okay so far? Okay. Design a gate logic, okay, I call the function S, AX, so that S1X is just X, S0X is the negation of X. This way we can redefine GI to be S, AX, the application of the function S, and YI, and then P is kind of the same thing, or YI. And let the input pin A determine whether the circuit should be acting as an adder or it should be acting as a subtractor. So are we still understanding the question up to this part, or are there any questions about it?
Are we recording?
I believe so. Question?
The
A is basically a variable or a parameter that is given to the function S. So S is basically going to be implementing a unification circuit so that we can use it for adding and also use it for subtracting. So the most important part is how I define the behavior of S, the function S. The function S, S1X is just X itself non-negated. If I use 0, it is negated. So that is the most crucial part. So we'll talk about how to figure that out later. Part A is to define the function S either as a Boolean expression or as a logic gate circuit. So it is up to you to choose. Okay, if you feel more comfortable with using logical expression, then go ahead and use logical expression to express it. On the other hand, if you feel more comfortable with the AND gates, OR gates, that sort of thing, then you can also express it as a logic gate. So as long as I can understand it and it is correct, you get all the points. So, and you may use AND or NOT gates, and you can use as many gates as you wish. Is that okay? So, how do we answer part A?
We give some kind of Boolean expression or a diagram of S, right? Is that what you're asking for?
Mm-hmm. Yep. Okay, so to answer A, the best way you can do it is to use a table. Okay, and it's not the only way to do it. It is one way to do it. So let me get to the notes here. Okay, and there we go. It's just being slow.
All the resources are being used for the incident.
Nah, just look at the lockdown. They got to be in.
And then, if there ever was a
Well, they didn't say it's a lockdown. If they had said it's a lockdown, then we would have canceled class and gone home. Okay, so let's go ahead and take a look at S1x and S0x, and then x is over here. So x can be 0 or 1. Okay, when x is 0 and a itself is 1. Okay, we want, I think the question says this one should be, okay, let me just double check because I don't want to quote myself incorrectly. It would be the non-negative version of x. So in this case we get 0 and 1 back. In this case we get a negative version of x, which is 1 and 0, like that. But this table is misleading because it looks like we just got 2 rows, but we really should have 4 rows. So the best way to do this is to look at x as an independent variable. Look at a also as an independent variable. So this way, you can now say, what is S of AX? And then we can define all the possible combinations. Like that. And then we backfill this particular table. Okay, 0, 0, 0 is a 1. And then that is a 0 here. This is a 1. And that would be
0.
That would be a 0. No, that's a 1.
Oh. Wait, yep, 1.
Okay, did I mess up?
Nope.
Okay, A determines whether x is negated or not. So x, okay, so let me use this one here.
I think if you highlight what A is in your original table, it might help. Like, so highlight the 0 and the 1.
Yeah, this is A,
Yeah.
and that is A as well. But the truth table may not be correct. Okay, so this is negating. This is negating x is 0, so it's negated. The negated version is 1. That's correct. This is negating as well. So x is 1, so the negated version is 0. This is non-negating, so I got this one wrong. There we go. Okay, that's better. So I messed up. I got that one incorrect.
Is it 0?
That one should be a 0 because when A is a 1, it is non-negating. So we just get x back.
So it's just an AND gate.
Hmm?
So it's just an AND function.
When it's 1.
Well, it's not an NAND because an NAND is asymmetric. The table wouldn't look symmetric like this.
Oh, yeah.
So there's only one gate or relatives of that one gate that can give you something that is kind of like this. If you flipped all the 0s to 1s and all the 1s to 0s, what would this table become?
Exclusive OR.
It's exclusive OR. So this one is actually the negative version of exclusive OR. Okay. So SAX. Okay. If you want to, you can define it like A exclusive OR X, but then you have to negate the entire thing. So that's one way to define it. There's one more way to define it. You can also define AAX based on the 2 rows that we get 1s as results. The first row is when x is 0, A is 0. So not A and not X will give us a 1 for that particular row. So not A and not X is going to be responsible for the first row where the result is a 1. And then the last row is also giving us a 1 as the result. But in that one, we just have the non-negative version of A and the non-negative version of X. So either one is acceptable as a correct answer because they actually do exactly the same thing. So do we have any questions about the answer to the first part of this question?
Is that like a De Morgan's law that transfers the top statement to the bottom statement, and how it changes from XOR to regular OR?
It's a separate statement. So
Yeah, it's completely separate. It's derived differently.
Okay.
The first one is based on the observation that if we flip the 0s and 1s in the result column, we get exclusive OR. So then we discover, we can just do the exclusive. We can do the negation on the exclusive OR to get to A. The second row, is using an entirely different approach. We're looking at the rows where the result is a 1, and then we come up with a conjunction so that the values of X and A of that row will give us a 1 just for that row. And then we OR all the different ones.
They contain the same logical output, but they don't have any Boolean algebra that can connect them.
Not as far as I know.
Okay.
Mm-hmm. Okay, so are we okay so far with this? Okay, excellent. So now that we got this part done, we move on. So we got part A done. Part B is asking, we know that a dedicated 3-bit adder needs 5 levels of gate propagation to finish computation. After unifying an adder and a subtractor using this approach, how many levels of gate propagation do we need for a 3-bit adder subtractor? And explain your answer. Okay, so the whole idea of carry look ahead and also borrow look ahead is regardless of how many bits we're dealing with, they always have the same level of gate propagation. So the question now is, what is considered a gate propagation? So gate propagation looks like this. Well, the levels of gate propagation. So in this case, if you still remember your K2, K3 circuit, okay, they look like this. They need the P's and the G's, right? So you have the first level of stuff, okay, to compute the P and the G's. So you have X, Y, and then you have G coming out of this one. And then this is an OR gate where you have X, Y coming in, and then you have P coming out of this. And then the last ingredient you need for everything else is K0. But K0 is an input pin, so it doesn't really have a cost in terms of gate propagation. So you have at least one gate propagation because of the computation of G and P. Okay. And then the next thing we do with all of these things is we have the first level of conjunction stuff. So you'll remember when you designed your 3-bit adder, K3 looks kind of complicated, right? So you have multiple conjunction gates, and then you have to split these wires, okay? And you'll feed those into these individual things, okay? Now this is not correct, okay? I'm just using this as an example, okay? But the result of the ANDs go to a single OR so that you can compute the carry. So right here, based on what we're looking at, we are already looking at 1, 2, and 3 levels of gates. Is that okay? But it's only computing the carry bits. We don't, except for K3, the most significant carry, all of the other carry bits are only used internally because we need to compute the sum, and the sum needs the XY exclusive OR so that they become the Q term. So that's why when you look at the whole thing, we have the same XY coming in to a exclusive OR gate. And then we take the output of the exclusive OR gate, and then we take the output of the carry bits, and then that in return is exclusive OR one more time to give us the sum when we're dealing with an adder. You guys still remember this part? So when you count the number of gates, we have 1 level, 2 levels, 3 levels, and here's 4 levels. But that depends on also how you implement exclusive OR. If you do not use exclusive OR and you use the conjunction followed by disjunction, that will also make it a little bit longer. Okay? So now the question is, if I introduce one thing and so that we can unify the adder versus the subtractor, is that going to introduce another level of gates? That is the question. Okay, so let's go back to look at how what that's going to do. Okay, so when you look at this part here, this is just X, and this is also X, and this is also X, right? But with the unification circuit, what we are doing is we are putting in an extra circuit here that also has a parameter of A. We're putting an extra circuit here with an extra parameter of A. So that what we feed into the conjunction to give us all the G term, and also what we feed into the disjunction to give us all the P terms, now we have an extra gate ahead of this particular input to serve as, should we negate it or not? Is that okay? So as a result, the number of levels of gate propagation should increase by 1. Yep.
Does that bottom X give it to?
No, that one is unaffected because this one is just giving us Q, and Q is the same whether you're dealing with an adder or a subtractor. So this one does not get affected. And even if it does get affected, it doesn't introduce another gate propagation because this is the shorter path. So we can actually introduce additional gates here and not impact the overall time needed to compute the sum or the difference. So is that okay so far? So the answer is, it would be one more level of gate propagation compared to a plain adder or subtractor. And the reason why we need one more level is because this has to be in here between the input pin X and also the input pin of the AND and also of the OR gate. And this is already the longest path. It's along the longest path, so we are making the longest path one level longer as a result. So is that okay, or do you guys need more clarification of this? No question. It's all good? Okay. All right, so let's move on to the next question. Question number 2. Question number 2 is also worth 4 points. Complete the following long subtraction. Specify all the borrow bits as well as the result bits. And the short form of this is 10101 minus 1011. And in this case, I give you a table to fill in. So use the table that is already provided to fill in your answer. Okay, what do you think? This one shouldn't be too bad, right? 1 minus 1 is a 0. 0 minus 0 is a 0. And because none of these two subtractions yields a borrow of 1, the borrow from the next column is going to be a 0. 0 minus 1 is a 1, and that gives us a borrow of 1 already. So we can fill this one here. 1 minus 0 is just a 1. 1 minus 0, once again, is a 1. Oops, is a 0. 0 minus 1 is a 1 with a borrow of 1. Yeah? Oh, that's a 1.
1 minus 0, that's you.
Yep. That's a 1, so this is now a 0. And neither gives us a borrow, so this borrow will be a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. Is that okay? But you also have to state the flags after the, this is supposed to be a subtraction. I obviously copied and pasted from the semester before when it was an addition. And forgot to change one of those. Okay, so this is a subtraction. What do you think is the overall borrow or the borrow out of this subtraction?
1.
Yep, that's a 1. So we put 1 here. What about the sign? The sign is always referring to the sign of the result, okay? The overall result. In this case, it's the difference because we have a subtractor. Is that a 1 or a 0?
1.
It's a 1. Very good. And what about the overflow? In other words, is the sign line? Does it make sense? We are subtracting a negative quantity from a non-negative quantity, but the result is negative. So is the sign of the difference making any sense?
Yeah.
No.
This is non-negative. This is negative.
It doesn't make sense.
So we are subtracting a negative quantity from a non-negative quantity.
So we overflow.
But we end up with a negative quantity. It doesn't make sense. So the overflow flag should be a 1. You can also plug in the equation. There is a logical equation for the overflow flag. Okay. So at this point, right now, you guys can ask, okay, where is that? It is in the comparison module. But in the test, you cannot ask me. Because it's in the notes, and it's open book and open notes, right? So you are responsible to bring whatever material is necessary to help you remind you of the definitions, the equations, the expressions, circuits, and stuff like that.
The overflow is on February 5th, if you guys want to look at the stream.
Okay, thank you. That is helpful. So now that we know the sign, reported sign is 1, but it's lying, what do you think is the actual sign? It's a 0. In other words, the L flag is defined to be the exclusive OR between the sign and the overflow flag. One exclusive OR with 1 is a 0. That's the definition of exclusive OR. So that's, I think, the second question. Yep.
Sorry, can you explain that one more time?
Yeah.
Say that one more time.
Can you explain that last part one more time?
The L flag is the exclusive OR between the sign and the overflow. So 1 exclusive OR with 1 is a 0. Because exclusive OR says, the two things, they have to be different. So is that okay so far? Okay.
Excuse me.
Yep.
What if you have addition? What would the overflow be?
Okay, so when you have addition, the overflow is still indicating that the sign doesn't make sense. But then the expression will be different.
No, but how do you know if it's an overflow?
Okay, so let's think about it. So you're dealing with addition. I'm going to go back to my tablet. And let's scroll this a little bit. There we go. So you're dealing with an addition. And you have 4 different scenarios, right? So we are only looking at the most significant bit here. So you have a negative number plus a negative number. If you have a negative number plus a negative number, what can possibly be the sign of the sum? It can go either way. Oh, I take it back. I take it back. It has to be negative. Okay. So, but what if it is not?
Then it's overflow.
Then we have overflow. So this is an overflow scenario for addition. What is the other overflow scenario for addition? You have a non-negative number.
Plus a non-negative.
You add a non-negative number, and somehow you end up with a negative number. That is also overflow. So based on this observation, we call this x, we call this y, we call this sum. Okay. So when you look at this, x m y m, but the negation of sm explains this one. And then you have negation xm, negation ym, sm, that explains this one. And then you have an OR in between because both of these are specifying overflow conditions for addition. So the equation is a little bit different from the one that we use for subtraction. And just frankly, we don't use overflow much after an addition. Even though it is defined for most processor, it is not usually used. The only time I can see how this is utilized is when you use a scripting language like Visual Basic. In Visual Basic, if you perform an addition and the sum actually cannot be stored given the number of bits, Visual Basic would not just silently let you do it like C and C++. It would actually complain. It would generate an exception, and it would be reported. So that is when it comes in handy. So we all good? Okay, thank you. The door was locked, right? So he has the key. He's an employee.
He's the murderer.
Yes, but he really should have been careful and go like, I'm an employee, do not attack me. I'm not the perpetrator. Because I got pepper spray right here. Although I cannot really quite shoot it this far, everybody in between from here to there will probably be crying for a while.
It sounds funny, man. Use that in Davis.
Hmm?
He since they get the one that bear sprays, the bear mace. I said that's not funny because in Davis several years ago, they actually did that to a group of protesters where they sprayed bear mace over everyone's face and they sent like.
And then they did a second round too.
Yeah,
I think
you know what I'm talking about. Yeah,
Yeah.
It was horrible.
Wasn't it for the rally or something like that?
Yeah,
It was like Occupy. When
Yeah.
Occupy was going on.
Yeah.
Wasn't he doing that like super like casual walk? Like
Yeah, no, he
Just
was like
walking
enjoying it.
close.
So it was pretty sick. So yeah.
Well, police in Davis really normally have nothing, absolutely nothing to do. So when they get a chance, sometimes I guess they go a little overboard. Oh, they catch people on a bike without a bike light. They give you a ticket for that. Or if you speed on a bike, they give you a ticket for that too.
I must have been really good because I never got a speeding ticket on my bike, and I never rode the speed limit.
I'm fast enough that I have never gotten the speeding ticket.
I had a race.
And I was on when I was at Davis, my first bike got stolen. Is a mountain bike. So I decided I'm just going to buy a female bike, with a bar that is kind of across diagonal, because it's less desirable, so it's not likely to be stolen.
Right.
So that one was never stolen, but it was a really nice bike. It has all the best components, on it.
You lucked out. No one was desperate enough.
So here's question number 3. Assuming the use of 2 input exclusive OR and OR gates with optionally negated inputs where the latencies are 4, 2, and 3 nanoseconds respectively. What is the total latency to compute K3 in an optimal 3-bit carry look-ahead adder that has an overall carry bit?
Did we ever go over this?
Hmm?
Did we ever go over this in class?
Well, the lab should lead you enough to figure out the answer to this one. Okay. Well, I just showed you the picture earlier.
True.
It is the same thing. Okay, so let's go back to that picture.
So you just add up the latency.
Exactly, you just have to add the numbers.
That's
And so latency is just the amount of time it takes for something to occur.
Right, so the latency is basically the delay from the input changing to the output changing of the same gate. Because it's not instantaneous, okay? Because remember,
Right,
a
so when I
NAND 2
change the
gate,
input, that's how long it takes for the output to change.
yes,
Yeah.
that is the latency.
Okay.
And you can remember that the NAND 2 gate itself is implemented in 4 transistors, right? So now the question is, how come there's a delay? I mean, I thought all of these things are pretty much instantaneous. So where do you think that latency is coming from?
The mechanical action.
There's no mechanical, it's all
Or the
electronics.
electrical.
Yeah.
It has to do with the capacitive load of a field effect transistor. Okay, if you still remember, okay, and most of you probably do not, the symbol of a transistor looks like this, right?
That's an N gate.
Well, I didn't indicate the direction, so it can be N or, right, because there's a lack of a bubble.
Yeah.
So it's an N type. Okay, so when you look at this, this is a transistor, but when you look at a capacitor, it has a symbol of that. Okay, this is a capacitor, this is a transistor. Do you see how this portion looks about the same? There's a gap between the two things. So this is capacitive. This is capacitive. A capacitor obviously is making use of its capacitive capability to do whatever it's supposed to do. For a transistor, this is a side effect, but it turns out to also have a capacitive property. When you want to change the gate voltage, it has to charge this plate, to the point where it starts to become a 1 or 0. So it takes time to charge that plate, and that is why it has latency. This is also why when we reduce the size of transistors, they become faster. Okay? Because when you think about this, okay, so let's say this is 2 scale, okay? And then we have a tiny little transistor here, basically the same design, okay? This plate is a lot bigger than this plate. It takes more time to charge the larger plate to the same voltage compared to the smaller one to even the same voltage. So that's why when we reduce the size of transistors, they also go quote unquote faster. Is that making any sense?
Mm-hmm. Thank you very much.
Yep. All right, so getting back to this picture. Now, question number 3 does not take this unification circuit into consideration, so we don't count that one. So now we just have to put the numbers here. Now there's a trick to this whole thing. And let me go back to question number 3. So 4 nanosecond applies to exclusive OR. So we'll just go ahead and put the 4 nanosecond here. There's a 4 nanosecond over there. And there's a 4 nanosecond over here as well, but that is not really the issue, right? Because the exclusive OR to compute the Q, it can be a lot slower, and it doesn't really matter because the other side of the input to this final exclusive OR has a lot more stuff going on, okay? But we're gonna put those numbers in anyway. And then we have 2 nanoseconds for AND gates, conjunctions. So we look up all the AND gates. We have 1, 2 here. And now this is the part that gets a little bit tricky. Because one of these, or I should say 2 of these AND gates are not only having 2 inputs. Okay. Do you guys remember? Because we're trying to figure out K3. When you try to figure out K3, 2 of the 3 conjunctions one involves 4 inputs, the other one involves 3 inputs. And then that's one that only has 2 inputs. So let me point out what I mean by that. So let's go back to the notes. So we'll go back to modules.
So each type of gate has a different latency, is that what you're saying?
Yep.
Yeah.
Each type, but we are also limited to only use 2 input gates. So you cannot have a 4 input gates to take care of, the conjunction that has 4 variables. You have to somehow break it up in a very optimal way to minimize the amount of latency. So, but before we go there, it is helpful to point out the equation itself, and then we can go from that and go like, okay, so how do we do this and having the least latency? Okay, so you can print out all of this stuff. You can print out the logic sim designs and whatnot. Okay, so we want to look up K3 because K3 is the one that is in question here. So we keep looking, almost there. So K3 is right here. Look at this conjunction here. It has got 4 inputs, but it is not allowed. You cannot use a 4 input AND gate. The question specifically said that you can only use 2 input AND gates. So how do you deal with this conjunction that has 4 things? You have to break it up into 2 levels, okay? P1 and P2 can be done first, and it can be shared between this term and this term. P0 and K0 will be done separately, but they can be done at the same time. Once you have the result of P1 and P2, and you have the result of K1 and P0, then those 2 will be ANDed together. So we need 1 more level of gates to do this. Okay, let me see if I can draw this picture here. So I'm gonna draw it on the tablet and then switch later. Okay, so this way you can see the equation while I'm working on the gates. And we have P1, P2, and then the other one is P0, K0. Okay. And then the other one has just an G0 by itself. Okay, so let me switch back. There we go. So when you look at the top part here, okay, I'm sorry that I have to make it kind of small to kind of fit the screen here. So we have P1, P2 going into this particular 2-input AND gate. We have P0, K0 going into this 2-input AND gate. The output of the first AND gate and the output of the second AND gate are connected to the inputs of a third AND gate. So the output of the third AND gate is technically the conjunction of the 4 inputs that we need. So we have to bump up the number of level of gates by 1 in order to accommodate this limitation. Yep.
And you did that because of limitation, because the two.
Yes, because theoretically speaking, we can say, oh, we can have a 64 input AND gate, but in reality you cannot have that. There are many restrictions, physical limitations, as to why you cannot have that. So that's why we have we call this a fan-in ratio limitation, because it's the input and it has to do with how many inputs can be utilized in a particular gate. So AND gates have a propagational delay of 2. So here's 2 and here's 2, but this whole thing, okay, is really doing this gate here, or one of those, okay. So one of these, 2 of these will have a 4 nanosecond delay. The last one is a simple 2 input AND gate, so it will still retain the 2 nanosecond delay. Is that okay? I'm putting the 4 here because this one boils down to this. This one, which is supposed to have 3 inputs, is going to boil down to this guy and also that guy. So it still has a total of 4 nanosecond delay. Is that okay? All right. So then we have one left. Okay, we have the OR gates. So the OR gates, this is one OR gate right here, and there's another OR gate here. But we also have a similar problem. This OR gate has multiple inputs, more than 2. And if we look up the actual equation, it has 4 inputs, which also means it has to be broken up into 2 sub-OR gates, and then the output of the 2 sub-OR gates will be ORed together to become the actual output. So that basically means the OR gate, the overall output OR gate, is going to be 3 times 2, which is a latency of 6. Is that working okay so far? So the restriction of we can only use 2 input gates actually is pretty severe as a penalty. It incurs a penalty in terms of the overall propagational delay. So now that we have all of these numbers, what is the actual propagation? So you have to be careful, because when things are occurring at the same level, you have to pick the one that is the longer. In other words, even though this is only taking 2 nanoseconds, this is taking 3 nanoseconds, and we cannot do a single thing until the output of this OR gate has settled. Okay? So of the first level, we take this one as a 3. At the second level, we look at all of these conjunction gates, and 4 is the longest. So we have 3 plus 4. Okay? At the last level over here, this is 6 by itself, but it has multiple inputs. So we have to take the longest path, so we have to add 3 to 4, and then to 6.
A question. So it appears the way you drill in this diagram that our Q, which is the bottom X exclusive OR, is at the same level as this 3 times 2, this double OR thing, right?
That is correct.
So when we did a comparison and figure out the longest path, we'd have to do both of those latency, right? Or no?
You mean between this OR and this exclusive OR?
Would those be considered? Would you have to take the longest one out of those 2 because they're on the same level?
Yep, we have to take the maximum of those 2.
All right.
So the top one obviously is much longer than.
But we have to make sure we consider that one in the calculation.
Yes. Yeah, we have to consider that one, but this one is obviously a lot faster because it is a single level of gate.
Okay.
So the total latency is going to be 3 plus 4, which is 7. 7 plus 6 is 13. 13 plus 4 is 17. So it will take 17 nanoseconds from the time that you are presented with X, all the bits of X, all the bits of Y, and K0, to the time that the sum bits are actually correct. I mean, the sum bits are always going to be there. There's always some kind of voltage at the sum bits. The question is, when can I count on those bits being correct? So it will take 17 nanoseconds to do that.
Is that long or short in your time?
It's hypothetical. So are there any questions about this analysis? The trickiest part of this analysis is the restriction because of the use of only 2 input gates. So that I think is the most tricky part. And then the second trickiest part of this whole thing is if there are multiple inputs to one gate, you have to compute the delay based on the longest path. Yep.
So you assign 3 based on, because it's an OR gate, the 3 nanoseconds because it's an OR gate?
Yep.
Okay.
But you have 2 levels.
Okay.
Because each OR gate can only have 2 inputs. That's part of the restriction in the question. So when this OR gate is supposed to have 4 inputs, now you have to break it up into like 2 OR gates to take care of the first 2 inputs, and then another OR gate to take care of the other 2 inputs, and then the output of the 2 sub OR gates will go to another OR gate to do the disjunction of all 4 inputs.
Is the number of nanoseconds per gate something you're going to let us know on the test, or is that something we're going to have to?
It will be presented to you like in this question. So in this particular question, it is a part of the question. So where is that? So right here it says 4, 2, and 3 nanoseconds respectively for exclusive OR and OR.
Okay.
Yeah. So it has to be given to you.
Okay.
But that's only if I decide to ask a similar question. Are there any questions about?
Now show your reasoning. That would be either a diagram or a Boolean expression?
I would use a diagram.
Okay, so you want circuitry for this.
Yeah, a diagram will help you analyze the whole thing too.
Okay.
If you break it down into a equation or expression thing, that will work too, because what you do in that case is
You still kind of diagram it out, huh?
well, the diagram helps to help you find the longer path. When you have 2 inputs to a gate, you have to take the longer path, as the delay. When you look at the expression, it doesn't tell you quite readily either. So it's not as effective.
Okay.
But you can always do the expression first and then turn it into the diagram. Okay, so here's question number 4. So this is a floating point question. We have kind of covered enough floating point stuff. Did I say anything about including or excluding floating point?
You said you were not going to include floating point.
Okay, so it is excluded.
Yes.
Okay, so we can
Because we
skip
just
question number
covered
4.
it last class.
We'll save it for exam 2.
Unfortunately, we will have to.
So it's neither good news nor bad news. It simply is, it's not in exam 1, it's going to be in exam 2. Okay, here's question number 5, which is the last one, which is also a double floating point question, so that one will be skipped as well. Okay, so based on the 3 questions that we have gone through, are there any questions? You really have to know your carry look ahead mechanism, the flags, how to compute those things. Other questions that I have asked in the past is, it is known after a certain calculation that the sign flag is a 1 and the overflow flag is a 1 as well. It is after subtraction. Give me an example of inputs that can make that happen. So I can ask questions in the reverse way. Okay, instead of giving you the numbers to subtract and then ask you what is going to happen, what is the borrow, what is the carry, what is the borrow, what is the sign, what is the overflow, I can reverse the whole thing. And I say, this is the result, okay? These are the flags of the result. Give me an example of what kind of input can make this happen. There was a hand earlier.
I was just gonna say on your diagram, the last one we did,
Yep.
that one part where you had the smaller diagram in the top right corner.
This one.
You had the arrow pointing to the AND gate with the 4.
Yep. Because
you weren't saying you replace that with that diagram up in the top right, were you?
Yep, that's what I meant.
Oh, okay.
Because this one, okay, so this diagram is not entirely correct, okay? Because one AND gate has 4 inputs, the other one has 3 inputs, but both of these cannot be done with a single 2-input AND gate. So the one that has 4 input has to be replaced by this particular design that has 3 AND gates and they have to be connected in this way. but the overall delay is instead of 2 nanoseconds, the overall delay because of the 2 level of the AND gates is now 4 nanoseconds. So from the perspective of the schematic, if I'm lazy, I can just say this is a quote-unquote single AND gate with 4 inputs, but then the propagational delay is now 4 nanoseconds instead of 2.
Okay, that makes sense.
Question?
Yeah, same with the OR gate as
Yep.
well. That there's 3 OR gates with 2 nanoseconds each, or is it the other way around?
Which OR gate? This one?
Yeah. Oh, it's 2 because then you have
Yeah,
one. And
it's
then you have
3
another.
times 2. It's the same deal because you have 2 first level OR gates, and then the output of the first level OR gates feed to the second level OR gate. So that's why your propagational delay is staggered, like 3 plus 3. So that's why it's 3 times 2.
Gotcha.
All right. Any other questions?
So we get and
I won't ask you questions about proofs, okay? So there's no need to worry about, proof type of questions. But just kind of keep in mind that I might ask you questions based on, after a particular operation, the sign flag is a 1, the overflow flag is a 1, and the borrow flag is this. What kind of input can make that happen?
And so an overflow flag can occur
Mhm.
on an addition as well as a subtraction, right?
Right, but since I never really give you the expression for the overflow for addition, so it will have to be given in the
Subtraction.
question itself.
Okay.
So I can say, okay, the overflow for addition is as follows, okay? So once I give you that equation, then you can use that piece of information. Okay?
Are we going to draw the transistors?
No.
Okay. I did that for nothing.
Now the transistor stuff it's really it's important in the sense that it completes the whole picture, because otherwise we'll still be boiling that things down to logic gates, but then it's not physical.
Mm-hmm.
Knowing that NAND 2 gates can boil down to 4 transistors is mentally or conceptually really important, because now we actually connect what we can do using logic gates to physical devices, and to me that is important.
That's how we make the computer.
Exactly.
what's the K knot attached to?
Hmm?
What's the K knot with the 2 nanoseconds?
Yeah, so the K0 connects to one of the gates. I cannot remember which one. So if you look up the nodes, it connects to, so K0 connects to the 4 input. So I got it wrong here.
Yeah.
So this K0 goes into one of the input here.
Okay. Oh, that's right. You said that it wasn't.
Yeah,
that.
but the K0 is not an issue because it's not the output of a gate. So it's not going to be on the critical path. It's not going to be on the path where you have the most propagational delay. All right. Yep.
For ones and twos, or carries, ones carry and twos carry, doesn't go any farther past that, right?
One's complement and
Or
two's complement.
Yes, I meant.
So that has to do with the representation of signed numbers. Okay, so what do you guys remember about signed numbers? How does that impact the circuitry of adders and subtractors?
It doesn't.
It does not. Okay, very good. Okay, that was supposed to be a trick question because because whether you're dealing with signed numbers or not does not change how we implement adders or subtractors. Okay, what have we discussed that actually pertains to whether numbers are signed or not? Comparison, but more specifically, what flags, okay, are important. So the B flag, the borrow flag, is useful for comparing what kind of number again? When do you use the B or the borrow flag to indicate whether the middle end is less than the subrahend?
Subtraction.
It's a subtraction, but signed versus unsigned. So when we use unsigned or signed values, that the borrow flag is useful. Which one is it?
The sign.
Is unsigned. Okay, so the borrow flag is useful when you are comparing unsigned values. So that will leave the sign, overflow, and the L flag to be useful only when you're dealing with signed values.
Right, okay.
Is that okay? But we don't have any actual instructions, or we don't have anything that utilize these flags at this point. So at this point, we're just defining the flags. We need to know how to compute the values of those flags based on calculations. But other than that, there's no utilization of those flags. Okay, any other questions? Now the labs can be useful. Okay, so I can either reopen all the labs, or I can give you guys like practice labs where it doesn't really contribute to your grade, but you can redo all the labs as many times as you want. I think that might actually be helpful. So I can do that. Next Wednesday is not the exam, okay? Next Wednesday is the class between the practice test, which is today, and the actual test, which is the Monday after next Wednesday.
Alright.
So if you study and you encounter things that you don't fully understand or you want clarification, next Wednesday would be a good day to bring those questions. And the nice part is you have a whole week to kind of collect all those questions before that class. Yep.
I was just gonna ask if next Wednesday was gonna be dedicated to that, or if
No,
we're gonna
it's
learn
not going to be dedicated to that, but if you do have questions, I will answer those questions first. If you don't have questions, then we kind of move forward with floating point number stuff.
I mean, sink or swim. Sink or swim, float.
Yeah, more or less. With this class, remember, what I'm going to test you guys on is not how well you can remember stuff, because it's open book and open notes, okay? It also pushes the responsibility on you to bring whatever you think is going to be helpful, okay? So even if something is, like a symbol, okay? So if I give you a circuit diagram, and it has, circuits or, gates like this, or gates like this, or gates like this, I'm not going to answer the question of which one is exclusive or, which one is or, which one is and, because you can bring your own notes to explain that, okay? So that kind of pushes the responsibility on you to bring whatever is necessary. So what am I going to test? Okay, what do you think, what do you notice about the questions that we have talked about up to this point?
It's all binary.
It has to do with computers.
It has to do with computers,
Wait, so are we
okay?
gonna have change your base in the test?
Sorry?
Are we gonna have change your base in the test?
Change the base.
Change the base.
Go from
Oh, you mean base conversion?
Yeah.
base conversion.
Well, it is in the scope, it's just that I don't have a particular question for base conversion.
Okay.
So those equations are in the notes as well. So
Right.
you know the methods of
You
doing base
practiced them in
conversion.
the first or second lab.
Yep. Yep. So that can potentially be in the test. So I'm not ruling that out. But when you look at just these three questions that we have gone over in today's in today's lecture, what do you notice compared to the material in the notes?
It's the same.
Mostly just applying the material in the notes into actual scenarios.
Yep. It is about problem solving using the knowledge that you have gained from studying the notes, doing the lab and stuff like that. But it's about problem solving.
It's fun.
Well, it's fun until you have a time limit, right? And the grade depends on it.
Whatever.
Okay, so
Okay, nonchalant.
we got about 4 minutes left. So I just want to kind of go over strategies that most of you know already. Okay. If all the questions have the same weight, it makes it really easy. Pick the easiest one to start with. Okay, that may be the last question, but if the last question looks to you like, oh, this is easy, I know how to do this, start with that one. And the second thing is time yourself. Okay, don't do it in a way that can disturb another student, but you might want to kind of keep track of time. Use a watch since your cell phone is not allowed. Use a watch, use a timer. Go to the Dollar Tree and get a timer for $1. Okay, but the idea is you divide the number of questions. You divide the amount of time by the number of questions, and then you give yourself some leeway, and then you just time yourself. Okay, if you cannot fully answer a particular question within the amount of time for one particular question, move on. I know it is difficult for some of you to say, but I'm almost there. Move on. Okay, because if you don't move on and you spend too much time on one question, it is possible that the next question is actually easier, but you won't have time to answer that question anymore because you have used up all the time in an earlier question. So you have to kind of, well, okay, this is how I would do it. How you want to do it is up to you. Okay, so how I would do it is I would time myself and I would just go like, okay, I've spent enough time on this one. I know it is not complete, but I'm going to move on to the next question. When you have time at the end of the exam, then you go back to the questions where you go like, okay, I know this one is not complete, or I know there's something wrong with my answer, then you work on that again.
Could you leave the lock screen on the computer when we have the test so we have the clock on it? That way it's on the screen? Or
Oh, you mean like here?
yeah, like how we show up every day, how it has the time on it when it's locked before you open it up? When it's on the
Over at the lab?
No, like a clock. You know how when you have the lock screen when you go to log
Oh, okay.
in? So just turn it on, that way we have a clock in front of us so no one's gonna turn over to that one.
I don't know whether that's good or not, because some people when they look at the clock, they get anxious.
Okay, that's fine.
So I don't know whether that's something that's okay with everybody.
No problem.
Okay, so here's another question. Do you want me to give you a warning when we are close to the end of the exam? And if you do want a warning, at what time?
30 minute,
15 or 30.
5 minutes.
30 minutes? And then 15 maybe?
Yeah.
And then a 5.
Maybe you can just
Okay.
update the time on the board like every 15. That's anxiety inducing.
Yeah, no.
No, you should have a countdown timer with beeps.
With-
It increases the frequency as it gets closer to the time.
and it has a red wire, a blue wire, and a black wire going into it.
And when you
Okay.
submit your test, you gotta take the wires and cut it.
Okay, but that
Okay,
brings
sorry,
up a good
thank you.
question. It brings up a
Thank you.
good question of whether I should ask the division to maybe buy a clock. Well, there's a clock, but it's kind of, you have to turn around to look
You
at
could
that
just put a
one.
mirror.
Huh?
Just a big mirror.
But then it'll be right side, left.
Or, go get a $5 Timex.
Timex?
You don't really need
Am I
the
that
time.
old, really?
No, I know what a Timex is. I know.
Okay.
Takes a licking and keeps on ticking. That is that Timex or is it Casio?
I think it's Casio.
Which one?
Timex makes the loudest watches. They are so loud.
Oh, you mean the alarm?
No, the
Just a
ticking
click.
sound.
Oh, the mechanical ticking sound.
Yeah,
I think Rolexes are so expensive.
Okay.
they're mechanical.
But you have to kind of have your own timekeeping instrument. I would just use like a kitchen timer that you can buy from, but make sure it doesn't beep. Okay. Because I don't need a whole lot of beeping at the end. But keeping track of time is important because I cannot tell you how many times I got people saying, I only worked on 2 out of the 5 questions. That is not good. Okay, because they missed 3 questions entirely, and those 3 questions that they missed can be one of the easier ones. Okay, so that's why I kind of want to emphasize, to kind of use a strategy to use your time wisely, because there's partial credit. Okay, if you answer a question incomplete, you might still be able to get some points, but it's important to move on and touch every single question so that you have a chance of answering every single one of those. All right. So we do have a lab activity tonight. It is related to floating point numbers and stuff. It does not need any extra discussion in lecture, and that's why you can still do that one. So we'll head out to the lab, and hopefully, we are not going to get any extra text from the campus police.
He's back. We got loose.
On the loose.